for p polarization, and this would be TM fields, if you like, okay, is equal to 2 cos theta incident sine theta transmitted divided by sine theta incident plus sine theta transmitted cosine theta incident minus theta transmitted. And there are lots of other ways to rewrite that. Just doing trigonometric identities make it easier to calculate. And the p reflection coefficient looks like this. Looks like that. Oops. I'm having the feeling that I dropped. Oh no, I didn't drop the minus sign. I kept one here. That's good. Right. What this one is telling us is that the sign of the phase of the reflected wave is negative. That is, that the phase switches sign. Not phase. The phase is pi. That the wave switches sign when it reflects off of a material for which theta incident is greater than theta transmitted. Using Snell's law is when the index of refraction in the incident material is greater than the index of refraction in the transmitting material, then theta I is going to be greater than theta T, and this term is going to be positive. And if this is positive, then the electric field switch sign. For the argument that I gave you with respect to, you got this field plus this field has got to somehow add up, and that means the reflected field has got to be negative, right? And that is included in this. You don't have to know anything. So let me work with the reflection coefficients now. Reflection for S, polarization, and P polarization. So now we can make a plot of the ratio of the amplitudes of the reflected wave, the actual coefficients, as a function of angle from the normal. So we're always measuring the angle with respect to the normal incident material. Okay. And what?
I didn't think.
Oh, I thought you.
The wind.
Right. So these are the Fresnel reflection coefficients, and perhaps I'll say one more thing here, which is that, okay, so I've got the amplitude of the reflected wave is equal to the amplitude of the incident wave times the Fresnel reflection coefficient. Have I told you the story of Fresnel?
No.
Has Schroeder?
Probably. Tell it anyway.
No, I won't.
We don't remember. Those of us who are in optics.
Okay, we'll do it during break.
Okay.
All right. Who said that? All right. Oh, you're talking about Schroeder's class.
I can't stay awake in his lectures right now.
All right. So that's the relationship between the fields, which means that if I worked out the intensity, which would be the average Poynting vector is proportional to the square of the fields. If I start writing out things in complex notation, then the way that you square the field is to multiply it by its complex conjugate. So that you get a real intensity by the time you're done. What I wanted to get here is that the intensity that's reflected is equal to the intensity that's incident times, which most of the time is just RS squared. And we frequently write that as intensity times the reflection coefficient of the surface. So there are the Fresnel coefficients, and then there's the reflection coefficient of the surface. So first thing, Fresnel coefficients. When I go and I plot this for a given index of refraction, let me choose n equals 1 and n prime equals 1.5, because that's glass. And that's the only one that I can remember off the top of my head. The S polarization reflection coefficient looks like this. Oops. As a function of angle. This is 90 degrees. That is, I'm just taking my angle from 0 to in the plane of the surface, 0 to 90 degrees. The S polarization reflection coefficient is negative, telling us that the phase has flipped, right? And it starts out here with the value of 0.2, which we can easily find, and we'll do that in a minute, actually, what the actual value is. And the P polarization does this. At 0, S and P are the same. All right? But if you look at what actually happens to that, and go up here to 90 degrees and 1, do that in advance. On that side, all right, it turns out that the P polarization switches sign. And what's going to happen is that it's going to look like that. Just plugging in the numbers, putting in the index of refraction, going over here, using Snell's law to find the transmitted angle as a function of incident angle. You just take that and you plug it in and calculate the reflection coefficient, and it looks like that. So normal incidents, they look the same. They have to look the same. Yeah.
And you said you take to get, or just thinking about I, to get I, you said you need to multiply E by its complex conjugate.
Yes.
But isn't the only real part of the field it says to take, like, if you look at Fertak and Klein, it says take the real part of the field to get the actual field.
Yeah, it turns out that you don't have to be as careful as they were. Then we're talking to like one person who's read one book, which is the better undergraduate optics text, not the one that you actually took your course from. They're very careful, and they are trying to make sure that the fields themselves come out right just the way that they want them to be consistently, right? And as a result, they're starting right off and saying, let's just take the real part. Let's be strict about the actual fields have got to be real. So we're going to take as our field either the real or the imaginary part of e to the I omega t minus kx, right? They're going to choose one or the other, cosine or the sine function. And they don't allow anything to be imaginary. It turns out that if, in the end, what you're going to do is, what you're interested in is phase, the phase relationship between two fields. If you allow it to just be complex and remain complex, and then when you're done, you take the ratio of the two fields, so the e to the I omega t gets canceled out, right? When you do that, you get rid of that, and you're left with a complex phase portion, which tells you how much one wave is advanced or delayed with respect to the other. That shows up for them in sine and cosine amplitudes, because the waves are always the result of the addition of a sine and of a cosine, right? But most of the time you don't have to worry about any of that, because what you're really interested in is the intensity, and that's the field times its complex conjugate, which is always going to be real. And it turns out that all of that e to the I omega stuff disappears, and you just get a simple intensity out. And by the way, the same applies to AC circuits when you use impedances, which I understand. Oh wait, only those of you who had Stoller for Physics 2 missed impedance. The rest of you got impedance. Lots of impedance from me. And now you've had reluctance too. The way that you deal with the fields there is that you should assume that the voltage is the real part of e to the I omega t, let's say. But you don't have to, because by the time you're done, you take ratios and the e to the I omega t goes out, and you're just left with phase shifts. Okay? So they did it to be pedagogical. I'm not.
In English?
Pedagogical, that's an English word.
Yeah, what's it mean?
Teaching.
It means do it that way.
Oh.
Okay.
Works fine. It means he read another book that did it in a slightly different way.
Okay.
And if you need to read Klein and Fertag, you're permitted to come ask me questions after you've read it. Okay, Fresnel coefficients look like this. Here's a weird thing. It goes through 0. Right at that point there, the reflected wave is has 0 amplitude for P polarization, has 0 amplitude. Many of you have heard about that point.
If that's 0, does that mean that
That's the Brewster angle. It starts at negative. Oh, sorry, at 0. Goes through 0. Since this was, I didn't label it, -1 and +1, then it ends up going through 0. Okay? If I look at the reflection coefficient, not the Fresnel coefficients, but what's called the reflection coefficient as a function of angle. That looks like this. 0.2 squared, remember this is glass, is 0.04. 4% at reflection intensity at normal incidence. And then for S polarization, it just goes up to 1. When you square it, it becomes positive and everything works out nicely. All right? For the P polarization, the reflection looks like this. Right there is the Brewster angle. Now, there's a neat explanation, physical explanation for what's going on here when you hit the Brewster angle. It's just a nice thing to remember, but it's not important to remember. And that is that if I think about the field in P polarization on the two sides of the interface, let me go over here. So I have my incident wave, and I have my refracted wave. Okay? And my electric field on, what am I going to do? Yeah. My electric field here points that way. It's oscillating like so. Now I get into, and now I've got my reflected wave. Incident and reflected. And I screwed up here. I want to choose a good angle that makes things look good. Look. Yeah, let's go like this. And then like this. And then for this material, that's going to go, yes. I had to cheat. Okay. So my electric field on this side is doing that. Okay? My electric field over here is doing this. What I've actually got here is a little oscillator. And remember how I talked about how when we talk about index of refraction, we have an oscillator here and the thing is oscillating and it is radiating. We're in the next class, actually we're going to start in this class, but next class we'll really get into radiating oscillators. So I've got an electron here that's responding to the electric field and the electron is oscillating. Okay? That electron is oscillating and sending out waves like an antenna. It's radiating this way. It's not radiating that way at all. You don't get radiation along the direction of the oscillation. Right? You don't get magnetic field along the direction of the motion of a charged particle. Okay? So over here, what you can think is that this reflected wave is actually the result of oscillations of the atoms, of the molecules, in the material into which you're transmitting. So let's say I've got vacuum out here, and I've got my incident wave coming in like so, right? The reflected wave is the result of the emission of the radiation from these oscillators. When the angle between the reflected wave and the transmitted wave is 90 degrees, I know that's supposed to be right angle showing there. When it's 90 degrees, there's no radiated wave from the material. That's the Brewster angle. So that's another way of remembering what the Brewster angle for a material is. Okay, yeah. So this can be very useful. This is the reason why when you're driving, you want to actually have polarized sunglasses, because if you're looking at the glare off the roadway ahead of you, then you're going to have reflection, which is over this entire range, typical range that you'd be looking at for reflection, would probably go from about here to here, let's say, from the sunlight off the roadway. And the P-polarized light has no reflected intensity, and the S-polarized light has got a fairly high reflected intensity compared to the P-polarized light. So if you wear polarized sunglasses that only admit P-polarized light, that is vertically polarized light, then you cut out all of that and you only get the glare off the surface from the P-polarized light, which is much, much less. How many of you knew that? No, not everybody. Optics. Did Schroeder tell you all about that?
At length.
Oh, yeah, that's right. Stealth technology, yeah.
Yeah.
I'll put that at the end of the course.
How he attempted to rederive like what the stealth coatings would have.
Okay. So let's see. Yeah, I've covered all the ideas up to this point. Next, we'll talk about complex index of refraction, or complex dielectric constant and the consequences of that. And that'll be the next part of the class, and then I'll just begin accelerating charges. Yeah. Okay. Break.